All right, section 5.4, last section of the semester. Woohoo! All right, binary trees and tree transversal. So we're gonna do two videos here. First one will be binary trees. So you've got some basic vocabulary: right child, left child, ordered binary tree, left, right subtree, and binary operations, operands, and then order operations. So these are kind of going to be in the first video as we kick off here. So here we go. So binary tree is in the event that each parent in a rooted tree has 0, 1, or two children, the rooted tree is called a binary tree. And so we'll take a closer look at what that looks like. But that's just our basic definition of a binary tree. We have left child and right child. We'll look at an example in just a minute. That's as simple as it sounds, is either on the right side or the left side of the root or the parent. We have an ordered binary tree. A natural order has been placed, a natural order on the children of each parent, and hence it has an ordered binary tree. And then we have a left subtree and a right subtree of the vertex. So those are kind of our beginning vocabulary words. All right, so let's take a look at those basic definitions of left and right child. So a left child of B. So we go to B and we're looking to the left, and so we see that D would be our left child. So if we're starting here at B, then our left child of B would be D. So check. If we're looking for a right child of F, so we go to F and we look to the right, and so that we would see as K. A subtree of A would be, so if we went to A and we looked at the subtree, then the subtree would be all of this out here. And so that can be listed in the sense that it will consist of the vertices C, E, F, I, J, and K with connecting edges. So those edges that connect that. So that would be a right subtree. If we did a left sub or a right subtree of E, so here's E. Wait, is that right? Yeah. A right subtree of E. Oh my gosh, I'm reading the wrong thing. Let me read the question instead of the answers. So let's do the right subtree of A. So right subtree of A, we just did that one, my bad, excuse me. Let's do a left subtree of E. There we go. And so we have E, and the left subtree would just be I. And then we do the right subtree of B. And when we look to the right of B, there's nothing. So then that would be considered empty. So that would be called an empty tree because there's no vertices and no edges. All right, moving right along. So arithmetic operations. So basically what we'll do is we have some symbols that we'll use for operations when we're doing binary operations inside of these binary trees. And so we have a plus sign, an asterisk will be used for multiplication, and then the up arrow will be used for exponents. Operands are the numbers or expressions on which the operations are performed. So the numbers or expressions we're operating on are called the operands. We can express an arithmetic operation such as plus or addition or multiplication or exponents in a binary tree by representing the operation as the vertex or the root. So for example, in this first case right here, if we wanted to look at x plus y, we would have x plus y. And so the operation, and then we'd have our two operands down here. So x and y would be our operands, and our operation would be the plus. If we wanted to do x squared, so x to the second power, we would have our two operands down here. So these are our operands on the bottom. And then we have our binary operation up here at the top. And so this would literally mean x to the second power. All right, so when an operand is an expression, the operand is represented as a subtree. So for example, if we had 2 plus x times y, would be represented in figure 3a. So this would be 2 plus x times y. Sorry about that. And so we would see that we have 2 plus, but because of order of operations, we know we're going to do the multiplication first. So we would have our x times y here. So then in our operation, this binary operation would come before we would do the addition, which leads us to a statement that we might as well go ahead and read. We build a binary tree that represents an expression from the bottom up. So you can see the x plus y, the x times y would come first, order of operations, and then we would do the plus 2 to that. We build a subtree for the first operation performed, then continue to build subtrees for successive operations until all have been represented. The last operation performed is the root of the tree. So remember, this is the root of our tree. All right, so the next one is 3x plus y raised to the second power. So order of operations would tell us we're going to do x plus y first. So x plus y comes first. So that's our first subtree. Then we're going to take that solution of x plus y and we're going to raise it to the second power. And then we're going to take that operation and multiply it times 3. All right, so writing our binary operations as a binary tree. Excuse me. All right. Let's make sure I didn't skip something there when I sneezed. Nope. Okay, so here we go. So cruising right along. So I kind of actually probably should have put this like little piece right here is that, our order of precedence of operations. So that's just order of operations. So AKA order of operations. And so going back and thinking about whatever method that you've used, these days kids use GEMDAS. And the reason they use GEMDAS is because G stands for grouping instead of parentheses. Interesting. And then exponents and multiplication and division and addition and subtraction. And so when you read these rules, it's really interesting because it says exponents from right to left. I never thought about that. So think about that for a second. Like if you had exponents from the right to the left, meaning like if I had x plus 2 quantity squared and then plus 3 raised to the third power or something like that, we would definitely work the exponents from the right to the left. So I've never thought about that, because I've always thought about working it from the inside out because it's a grouping symbol. But so it's interesting the way they list it, but it doesn't change anything. Our order of operations are still exactly the same. So with that said, let's take a look at our particular problem here. So in the algebraic expression below, we will represent exponentation with an up arrow. What is the order in which the operations are performed? So this is what we're trying to solve. So when we break this down, we've got lots of ways we can kind of attack this, and when you think about it. But the first operation that we might want to choose would be the x minus y. Then we would do the x plus y. So we would take care of let me just get rid of some writing on here. So maybe the first thing we would do would be x minus y. Then we would do x plus y. And then our exponents would come next. So then we would have our x squared, and then we would have our division coming in last. So how would that look if we thought about that as a binary tree? And so if we wanted to make a binary tree of that, what we would do is, let me move this out of the way. There we go. There we go. All right, so if I wanted to look at that, the first thing we said we would do is we would start to build binary trees that represented the operations that we needed to perform. And so the first operation we performed was x minus y. Got it. The second one was x plus y. Then we take the x plus y and we add on the raised to the second power. So basically we took this guy right here, and there he is right here, and we added on that we're going to take this and raise it to the second power. At that point, what we know is that we have our initial operation of x minus y, and then we have our second operation that we had, which was x plus y raised to the second power. And then we have that we're going to divide those two expressions to be able to get our final solution. So this would be our binary tree made up of the subtrees that would represent this expression right here. All right, I think that's the last slide. Let's take a look real quick. I think there's one more. I'm gonna hit pause for a second. Yep, that's the last one for our binary trees, and so we'll look at tree transversals next.